How caching works in a project. At its core, caching operates on a simple principle. Store data you've already computed or retrieved, so you don't have to do it again. Here's a breakdown of how it works in various contexts within a software project. When a request for data comes in, the system first checks the cache to see if the requested data is already there. Cache hit. If the data is found in the cache, it's called a cache hit. The system can then serve the data directly from the fast cache, significantly reducing retrieval time. Cache miss. If the data is not found in the cache, it's called a cache miss. The system then proceeds to retrieve the data from its original slower source, e.g., a database, an external API, or by performing a computation. Populating the cache. After retrieving the data from the slow source, the system stores a copy of it in the cache for a certain duration or until it's invalidated, so that subsequent requests for the same data result in a cache hit. Types of caching in a project, as seen in the provided project structure. Build caching, e.g., Gradle folder and Gradle's build cache. What it caches. During the build process, e.g., compiling code, packaging resources, Gradle can cache the output of tasks. If a task's inputs haven't changed, Gradle can reuse the previously built output from the cache instead of re-executing the task. How it works. When you build your mobile or automotive module, Gradle calculates unique keys for each task based on its inputs, source code, dependencies, configuration, etc. It stores the output of the task along with this key in a local or remote build cache. The next time you build, if the inputs for a specific task are the same, Gradle checks the cache. If a matching entry is found, it retrieves the output from the cache, making the build much faster. Benefit: dramatically speeds up compilation and packaging times, especially for incremental builds or when switching branches. This is why you often see large Gradle directories. They contain these cached build artifacts. Dependency caching, e.g., libraries downloaded by Gradle. What it caches. When Gradle resolves dependencies, like external libraries specified in build.gradle.kts, und it downloads them from repositories, e.g. Maven Central. These downloaded libraries are then cached locally. How it works. The first time you build a project, Gradle downloads all necessary libraries. It stores them in a local cache, usually within your user's .gradle directory or a global Gradle cache. Subsequent builds of the same project, or other projects that use the same libraries, will find these dependencies in the local cache and won't need to re-download them, saving time and bandwidth. Benefit: faster dependency resolution and offline build capabilities once dependencies are cached. IDE caching. .idea folder. What it caches. Integrated development environments, IDEs like Android Studio or IntelliJ. IDEA. Maintain their own internal caches to speed up various operations. This includes indexed files. The IDE indexes your project's code for fast searching, auto-completion, and navigation. Class files, compiled classes. External library indexes. Information about methods and classes in external libraries. Project settings and configurations. To load the project quickly. How it works. The IDE stores this data in the IDEA folder and other internal cache directories. This allows the IDE to provide features like instant search, code completion, and refactoring without constantly reparsing your entire codebase. If these caches get corrupted or become stale, you might experience issues, and clearing them, often an option in the IDE, can resolve problems, though it means the IDE will have to rebuild them. Benefit: enhanced developer productivity through faster IDE responsiveness and intelligent code assistance. General caching principles, applicable to any software project. Data consistency. A critical challenge in caching is ensuring that the cached data remains consistent with the original data source. If the original data changes, the cached copy becomes stale. Strategies like cache invalidation, removing stale data, or cache expiration, setting a time to live for cached items, are used to manage this. Cache eviction policies. Caches have limited space. When the cache is full and new data needs to be added, An eviction policy decides which existing data to remove. Common policies include least recently used, LRU, removes the item that hasn't been accessed for the longest time. Least frequently used, LFU, removes the item that has been accessed the fewest times. Where caching is applied, caching can occur at multiple levels. Client side, browser caches web content, HTML, CSS, JS, images. Application level, in-memory. Applications store frequently used data directly in RAM. Database caching. Databases themselves often have internal caches, and applications can implement caching layers in front of databases. Distributed caching. For scalable applications, a separate caching service, like Redis or Memcached, is used to store data accessible by multiple application instances. Content delivery networks, CDNs, cache static assets geographically closer to users to reduce latency. In essence, caching is about trading off some memory usage for storing the cached data for significant improvements in speed and efficiency by avoiding redundant work or slow data retrieval.